So, thanks for coming to the Starlight Seminar. Today we have two guest speakers. The first one will be Lowry. I think most of you know him. He was Professor Rutherford's PhD student before, but he has been a very recognized Starlight member for many years, and very well known by playing badminton, particularly his wife was the champion of Canada. So Mike, you want to give some more introduction about yourself? Go ahead.
Well, that's a great introduction. Although badminton and my name actually probably don't need to go together. My wife, on the other hand, yes, she is a badminton star, and she loves playing Yin Hai quite a bit. Yin Hai got me playing too. I was there every Friday with Starlight playing badminton. We're gonna play today too, if you want to join us. But by way of introduction, yeah, I'm really glad to be back to the University of Washington Sunday in Seattle. I'm now at the University of Idaho, which is in Moscow, and about 6 hours away. This image you see here is, wow, the quality is not too great. Are these lights able to dim at all, or no?
And we can turn the lights off for the whole.
Oh, okay. Well, we'll see. If we need to, maybe we'll do that. So that's Moscow right there, where I'm from. It's a small town, a lot different than Seattle, but a really beautiful place, and you're all welcome to come visit us over there. We have a University Transportation Center as well. NIAT is the name of our group there. We have 3 faculty that are in civil engineering department besides myself, so 4 total there. We're hiring 1 now, and then we have other faculty in mechanical engineering, electrical engineering. In fact, our research center at Idaho has quite a few real high involvement from these other fields of mechanical and electrical and computer science engineering. We are focused on technology. Well, I'm a planner. I'm sort of the odd duck over at NIAT because I do more planning issues related to planning. So the title of my presentation, Using Street Topology to Estimate Traffic Warnings. And I'm going to go over 4 tools that we developed at the University of Idaho. And I'll just go through them one by one. And it'll take about an hour to go through all of them, but I welcome your questions in between. I kind of accounted for that and everything. So the first tool relates to estimating bicycle and pedestrian volume. Second tool, estimating average annual daily traffic, and then estimating turn movements, and then estimating performance measures. I started off with the title is topology. So let's see if I can get some interaction here. You can tell I'm now a professor. I have to teach, so I got to engage my audience, right? So, who remembers what topology is? What is topology? Study of that's,
like topography.
That's topography.
Confusing.
Common, yeah, topography and topology. Who remembers what topology is? It's different. Remember? Topology. Well, here's to remind you. Famous mathematician Euler. He invented the whole field of topology. Topology is the study of spatial connections, of how space is connected, how whether it's streets or buildings. That's what topology is. And the famous mathematician Euler in 1735, he was living in this place called Königsberg. And is this ringing a bell? Does anyone remember the story of Euler and Königsberg and 7 bridges problem? Anyone know it? What happened?
Optimize the path route for the traverse the 7th bridge.
Yeah. Every day he walked to work and he crossed over these bridges, and he thought, how can I get to work crossing over every bridge without having crossed the same bridge twice? And a mathematician, so he he converts all of the bridges into links and nodes, and with that we have the invention of graph theory. So another way of saying topology is graph theory, the study of graphs and the connections of links and nodes. And so I'm going to use in my approach some of these techniques that started way back when with Euler's graph theory and topological research. This has been a huge explosion of graph theory in recent years because of social networks. A lot of the real cutting-edge work on graph theory right now is coming out from people studying, for example, the connections of the network of Facebook. And I just did some search of some interesting things that are out there. And this was from a paper that talked about these are connections of friendships, people that know people and then who they know. And they looked at different attributes of each of the individuals. And they found, for example, that obese people tend to be friends with obese people, and thin people tend to be friends with thin people. That's what this paper is about. They've done all kinds of research on how people are connected through their friendships or whatever type of relationships. This is another paper that I found. This is a representation of political blogs. So each node represents a political blog, and political blogs would, one blog writes what another blog wrote, and they're just sort of repeating what other blogs are saying. And this one in the middle, that's the bright red one, that was this Nate Silver's blog. I'm sure Scott knows. What's it called? He called it Nate Silver's blog, I'm sure. The New York Times, the recent election, and he was doing all kinds of really interesting things. Well, it turns out a lot of people were just repeating what he said on their own blog. This is some analysis that is being done. In terms of transportation, we can represent a street network as a graph or as a link node network, where each street is a link and each intersection is a node. And there's been a lot of things. Well, when we're looking at networks, one thing we want to do is we want to talk about maybe the importance of linking. So, like I was saying, the importance of these measures, these generic measures. One of them is called centrality. What this centrality measure is the measure of how important a node or a link is in the whole network. And there's actually quite a few different calculations of centrality. There's betweenness centrality, closeness centrality, degree, graph, and stress centrality. And they're just different mathematical formulas that give some sort of number to the link or the node network, to the link or the nodes, representing how important it is in the entire network. And this has been used in some transportation research. Just a few years ago in TRB, there was a project that was looking at betweenness centrality and calculating that for subway systems. Does anyone know what city this is?
DC.
Yeah, this is DC. And they did the betweenness node centrality for all of the subway stations, and they found that the higher centrality number is associated with boardings and alighting at that metro station. So that's an example of some research that's been done. Another area of this is actually most of the research on this has been with urban planners, looking at how cities grow. This is London over the years and how it grew, and they're using another form of centrality called space syntax. Anyone heard of that? Just to know my audience, okay? Because that's sort of the hot topic right now, is space syntax, but I have lots of problems with it. I actually don't think it's a really good way to go. But they use that here. This is measuring the centrality of the important streets in London over the years, and they as urban planners, they're doing it not for traffic reasons, but more reasons of maybe historical importance or the sense of space that's happening in the city. And so that's what this paper was about. It's about the sense of space and the importance of a street in the communities of London. So with that now, as introduction, I'll start talking about these 4 tools that we've developed. The first tool is a tool to estimate bicycle and pedestrian volume. And I need some real quick background on estimating bicycle and pedestrian volumes and how that's currently done. Does anyone have any idea of how we currently estimate bicycle and pedestrian volumes?
Send the internet to count them.
Wild guess, Mark said.
Send the internet to count them.
Yeah, that's how we're going to get our count, but then how do we estimate it or extrapolate that to other locations? There's actually not very many. There's really nothing. First off, let me split estimated bicycle pedestrian volumes into 2 categories. First is the category of just citywide mode share. And that's like we take surveys and travel diaries, and we get the general sense of how many, what percentage of this city is riding their bike or walking. And then the other is the facility volume. So actually, how many people are walking or biking on this particular facility? And we do that in 2 different ways. We do it in these really elaborate multi-step behavior models, which is commonly known as the 4-step model, right? So as an example, where we're trying to estimate so many different things. We're also estimating trip choice, destination choice, route choice, and mode choice and route choice. And by doing that, we've got this big model. And for example, here in Seattle, when I was a student, I took it from Larry Blaine. He's teaching that, of course. So he just Cynthia's it. Larry did a great job. I hope Cynthia did it too. I really enjoyed that classroom. But the biggest takeaway I got from Larry's class is that these models are extremely complicated. They take 8 hours to run one model, and they don't get very good results. So it's a lot of work, and they get even worse results in terms of bicycle and pedestrian. They don't get very good results for cars, but they're even worse for bicycle and pedestrian. In fact, lots of cities don't even include it in their model. It's too complicated. So the other way to do it is through a direct demand model. And this is where we take the attributes of, let's say, a facility, a street, and we say, okay, we know what its adjacent land use is, we know how wide it is, we know what the speed limit is on it, just a bunch of attributes of it, and we'll just use regression to say we're going to estimate that'll be the volume for this this facility. And this, for bike and ped, this is the most common way, but it isn't very good. In fact, the problems with these current methods is, as I said, the multi-step methods are very complicated, sophisticated. They usually require special software to do. The direct demand models, the thing that's missing there is that they ignore the origin-destination relationship of trips, and they ignore just in general the whole network's characteristics of trips. And most of the time, they don't even predict a directional volume. They just say this facility probably has 30 people biking on it at 4 in the afternoon, and we don't even know which direction they're going because it's not part of the way the regression was written. And it's also not very accurate. So our approach is, in a way, a mix of the two. And I'm going to explain how that is. You'll see how we're doing that. But it's going to account for the network. It's going to account for OD routing. And then it's also going to be a regression. So the way we do this is we're going to use one of these particular types of centrality that we stress centrality, and we're going to modify it. And before I explain how we modify it, I need to explain the calculation of stress centrality. So this image is showing stress centrality. And the red, this is the linked node network of Moscow. And the red streets have high stress centrality. The calculation, for all the people that love math, is quite simple. It's just if we say, take all of the nodes of the network and travel the shortest path from every node to every node, node I to j, and then sum up if, so then the sigma ij as a function of the edges of E will say that if that link is used, then we'll give it a full count. So it's just a number, summation of any E determinant. Travel from every node to every node and count how many times the link is used. That's called the stress centrality. And so the red means that those links are used more, and the blue means they're not used as much. So we're going to modify this for our purposes because we found that this actual calculation didn't work very well. So we give it a new name. We call it OD centrality. And it's a modification of stress centrality. And the modification it does is, first of all, we're not going to go every node to every node. We're only going to go from origins to destinations. And we'll call origins perhaps residential parcels and destinations commercial parcels. So we're going to define which nodes we're going to use. Second, we're going to weight those origins and destinations with a multiplier that represents some sort of level of attraction or trip generation rate. And then the third thing is we're going to do for bicycles and pedestrians is we're going to limit origins and destinations again by only those origins and destinations that are within a certain reachable distance. And we found it to be about 1.5 miles. People don't bike more than about 1.5 miles. And so that's what we're going to do. So our equation, again, so in terms of showing this graphically, we're going to define origins and destinations, like residential space perhaps, and then destinations as commercial. We're going to weight these. Origins right now we're weighting with the number of dwelling units, and the commercial space we're weighting it with the square footage of the parcel. And then the second thing we're going to do is we're going to limit the origin and destination to this buffer distance, what we're calling the reachable distance. So in the end, our equation is a modification of stress centrality, and there it is. There's not much of a change in terms of what the map looks like. The main change was in the node sets that are used, and then the multipliers that are added on. They're multiplying on. So let's go back and look at the two. The one on the left, and this is kind of a small screen for people in the back, but let me just see if anyone can see any difference between the stress centrality and our OD centrality. See any differences? What are some differences do you see?
There's no yellow in the OD centrality, very, very little yellow in the OD centrality. The amount of red is correlated right on that east-west or over that. So
yeah.
You lose a lot of the north-south quarters.
Oh, no. Okay, so here's John just used this for my pointer. Yeah, Mark noticed two things that we also noticed. First off, there's not as much happening up here, and second, it moves everything kind of more of the focus is to the left. There's reason for that. That's where the University of Idaho is. So what it did is it said that most of this centrality, more important, is closer to that heavy attractor. And then it also said there's not much happening up here. And the truth is, there really isn't. Not many people are going to bike from here way over there. So we found that there's not many people biking up here and pedestrians up here. This is all residential, in fact, sort of farmland up here. As we get out here is farmland, but it's lower density residential. So that did exactly what we wanted to do. And then what we're going to do then, our method is quite simple. So a practitioner, a city planner, who wants to estimate bicycle volume, first thing they got to do, collect data. And I'm going to explain how we did that. And then they're going to calculate the OD centrality. And then it's really simple. We're going to do a regression off of that OD centrality. We're just going to say that the volumes are equal to this regression line. And so the question is do we get good correlation with centrality to volumes? Now, for this presentation, I'm just going to talk about that simple equation. But we could have done more. We could have said plus maybe the functional classification of the road, plus the adjacent land use, plus beta times the, we could have other betas and other explanatory variables. But for simplicity right now, let's just talk about using only centrality to estimate the bicycle volume. Okay, so our observed data, we collected at 26 locations in 2011 and in 2012, the morning peak and the PM peak. So we stood out there and counted every turn movement that was happening. And other research on bicycle pedestrian research actually doesn't go as detailed as we did. So that's another thing that we feel really excited about. Because often what they do is they just stand at a street and count going in either direction. But we're a little more detailed because we actually have turn movements at every intersection. And so that's pretty good. We did this count actually not really knowing that we were going to go in this direction of research. It was actually part of the National Bicycle and Pedestrian Data Destination Project, documentation project. And who's familiar with that? Only Mark, that's what I thought. Mark, what is it? Can you say real quick?
Basically, we have counted bicycles and pedestrians so seldomly in this country, they were looking for guidance on how you might do it reasonably consistent. So the Bicycle Pedestrian Documentation Project looked at best practices, gave advice, best advice in the world, and encouraged people to go out and collect information on bike pedestrians and actually submit it.
That's right, and so it was done with ITE and also Alpha Planning, and I've talked with the folks at Alpha Planning, and they're really excited because they're getting data from all over the country, but the thing is, they don't know what to do. Because there's not really, they just, in a way, Lauren Ledbetter, I don't know if you know her, she's at Alpha Planning, but she said that in a way, part of this was to just get it started, sort of grassroots to get people to collect bicycle and pedestrian data. But now what? Now how do you use it? It's actually not in any of the documentation. So they talk about, well, now you know the volumes, but they don't, there's room there for, well, now what do we do with it? And we use bicycle pedestrian data, the way that it's organized and everything, for our tools. So that's another advantage of this. Okay, so I'm going to leave the presentation in a moment and show you it in ArcGIS. But really quick, I want to show you the GUI for this, and also to get a sense of my audience. Who's familiar with ArcGIS? Okay, and so a few of you, about half. But it's really great software, and what we've created is Python add-ins. We've written all the computer code, and they're just tools that can be added in and really easily. You actually can run them off your USB. They're simple to use. And all of the tools will have a GUI like this, and I realize that the screen is small, but let me just sort of explain. You've got input values here, and then you've got where's your output going to be down here, and then you hit OK, and it runs it. So let me go in and show you what we've got here. And got a little screen. So, just to remove these. If I was online, I have base maps that show. Well, I'll just leave it to explain that in a second. But here's the link node network of Moscow. And so what we have is, this is a really, and the other thing that's great about these tools is they use commonly available GIS data. Most of this was just from the city of Moscow. It was their street centerline file. And this was from their parcel file. These are the origin parcels, and they're just the residential parcels. And then these are the destination parcels. That's commercial and government land that we'll consider as an attractor. as destinations.
Like, where's the University of Idaho? It doesn't seem to show up given where you're circled.
It's all this right here.
But it's neither an origin or destination.
It is. It's in red. For the city of Moscow, for the university, we were able to use parcel files because a parcel file is the whole piece of land, and the university owns this whole thing, so it's actually one big parcel. So for the university, we actually are using building footprint. So we broke the parcels on the building footprint. But for everything else, we just left it as a parcel file. So for those of you who planning things, a lot of your operations, so that a parcel is just the the land owners, and since the University of Idaho owns the whole big piece of land, it was one parcel.
So when you weigh by square footage, are you weighing by square footage of building footprint?
For that one, we weigh by square footage of the building footprint.
So like the red dot and university campus does not represent anything actually the real attractiveness of the campus, right? Because you split that into smaller buildings. But for other pieces of the process, they're considered attraction. You put it you're already red.
Yeah, that's a great question. And a lot of you are getting to something that I will show in my presentation in a moment. We're doing research on what should that multiplier be. And actually the way we're dealing with that is we have the multiplier is the square footage of the parcel or the building footprint multiplied by a number of, well, if it's a park, then it's a reducer. So it's just reduced by a little bit. Or a commercial will be more. So we just have 5 different land use types, and it's like commercial and different types of commercial and the different types. And so, for example, you're right. This right here is actually just a park. So it's just green space. And so that one, we didn't actually do square footage. It's an adjusted. So I'm going to show you. In fact, I'll just open it up right here. So in GIS, you've got all the files, and then you can just right-click and open up all the attributes. Here is the area, but what we have is actually an adjusted area based on the type of land use.
Do you have access to employment data or something that would be?
That would be great. Yeah. So part of the research is, well, what should you use as your attractor multiplier for destinations and for your origins? And right now we're using, as I said, an adjustment of the square footage for the destination, and then we're using dwelling units for the origin. But there's definitely room for an improvement there, and that's part of the researching. Great question.
So if you're looking at head and body volumes, wouldn't it seem like some of the parks, like soccer fields, stuff like that, would actually have more? Yeah.
Yeah. So the other thing is so these are great terms. I actually figured that those are details that we wouldn't. So there's not really part of the presentation, but I'm glad to hear it. So those sorts of details, those sorts of things is part of the calibration, right? So you're trying to calibrate what should your origin to destination weight be. And we're actually finding that calibration also depends on time of day. So in the morning, you're going to want to wait for the morning commute in a certain way, and then in the evening, a different time. And maybe for your off-peak, yeah, you want your parks, your playgrounds to have a really high weighting.
And I think there'd also be a pretty strong seasonal component too, because you're probably not going as much in dead of winter in Idaho as you would be in.
That's right. Yeah, so remember, our data is a snapshot of the morning peak and the PM peak. But certainly, as you could calibrate this model for different data collection time periods.
It also seems like, particularly some of the parks, would have a longer distance that you'd expect people that your OG distance would be expected to be a bit wider.
Their willingness to travel to that?
Particularly
could be.
Sporting stadiums, stuff like that, where you might not necessarily stadiums.
That is an idea we haven't thought of. That's a good one. And perhaps adjust the reachable distance depending on what right now it's just a standard 1.5 miles to all destinations. But what you're saying is maybe you'd go 1.5 miles if it's a commercial, but you'd be willing to go 2 miles if it's a park. Yeah, that's a great idea. That would be one way to improve the model. So let me show you then how this works. This is the toolbox on the right. I don't have a lot of space because the screen is so small here, but the toolbox is you just bring them in, you run them off your USB, and that's the red. Here's the toolbox, and then we organize them into two what they call tool data sets or tool sets. So the first one is data preparation tools, and if I have time, I'll go over that at the end. Then here are the analysis tools. I'm going to go over all of these. There's one that just says calculate centrality, and then I have each one for the 4 tools that I want to go over. And so let's do this first one. Here's the interface. And it wants to know what is your account data. So we got to go here. This is my account data folder. I have 4 tools to show, so I'm going to try and be really quick with running these. Then it wants to know what's your input into your street network. And then we want to know directional, you know, because we have a few one-way streets in Moscow. So we have the direction, the allowable direction. And then this is the impedance field. And again, that's a detail that I can talk about if you want to more. But let's just say for now that for bicycles, we're just using distance. But you could also use speed or some other thing to weight the impedance on the link.
Slope would be a good one.
Slope, we looked at slope. I'll show you what we've done with slope. So then origin destinations, and then the multiplier. So again, we're going to use dwelling units. And then my destinations, we're going to do that. And then for my destination multiplier, as I said, we're going to do an adjusted area. So that's the adjusted area. It's not, like I said, it's just we changed it. And this is the buffer distance, and this is where I'm going to put in 1.5. That's the in miles. And then I could have additional explanatory variables, like I said, functional classification or something else. Maybe is it next to a pretty scenic byway or something. So we could add those, but I won't do any right now. And then I got to say, where's the output going to be? And we'll call this a bunch of test output right there, but I'll just call this bike volumes. Okay, and then, oh, oops. How can I?
Maximize it in the illustration.
There we go. So here we go. We run it, and this is now running. Let me just. It takes a few minutes. What this is doing actually is quite amazing. It's calculating now the centrality going from every origin to every destination. It's calculating that centrality. So it's calculating hundreds of thousands of explanations actually. And it's meeting the speed now with computers. Because when I did my master's degree like 10 years ago, I did something similar. And it took us overnight to run like not even half as many as this is doing. But this was just, it runs fairly quickly. It's calculating the shortest path from every origin to every destination. And then it's going to use that value in a regression to estimate the volume and all that. And here it goes. So now it's estimating volumes.
To develop the GIS program in Haizhong, you GIS platform, right?
Yeah, I'll show you that in just a second. So there it completed. It took about a minute to run, and here's the output. So is that let's see, is that clear what we're seeing here? These are the estimated bicycle and pedestrian volumes. So
Even the thickness of the line shows the volume level.
correct. Thickness of the line shows the volume level.
Are you enforcing any kind of continuity, as in, if you've got bicycles coming into a segment area, that they have to be conserved at certain locations?
No. Well, that's happening naturally though, because centrality was
Helping you.
yeah, that had a conservation of movement. So this has a conservation of movement. Yeah. So if you look at numbers adding up, yes, they do total each other. So yeah, I should say yes, we do. So like, let me just zoom in for a street here. This is down by the university. Again, I can open up the attribute table, and that's just some stuff, you know, the street names and everything. But, let me highlight this street here. So this street here, right here, estimated volume, this column right here. It's kind of hard to see. Can you guys able to see back there? Correct. Yeah, so it says it's 50. Good eyes. Really good vision. So 52. It estimated 52 bikes going that way. So I'm imagine Scott way in the back with his excellent eye. He can see that too, right? So what we have here, it says 52 going this way and 10 going that way. So it's not only we volume, but we got the directional volume. And as I say, that's an improvement compared to other methods that just say they would have actually just estimated 60 people on that road, and we don't know which direction they're going. But I actually have which direction they're going and where they're going to turn, an estimate of where they're going to turn. Yeah.
Those parameters, which instead of the distance, do you also look at the feeling of space? Yes, for that means.
We did, in fact. So in terms of our impedance, we looked at. Are you familiar with the bicycle level of service?
Yeah.
Yeah, it's a new level of service in the new highway capacity manual. And we actually have that bicycle level service, and we use that as well. That's part of what we're doing. let me go back to actually I want to open up the next tool while I'm or the next. Oops, because it takes a minute to load. Let me go to my presentation here. So, okay, so what are we currently doing? We're looking at improving the statistics. Maybe instead of the just normal ordinary least squares, since it's count data, maybe we should have something like a negative binomial or Poisson regression. And by compare, also probably maybe like a zero inflated regression or something. So we're looking at improving the statistics. And then, as everyone in the room seems to notice, is well, there's also some work that could be done on calibrating your origin and destination multipliers and calibrating your route impedance. Like maybe your route impedance should be something like you said, safety, because then it's going to send people on a different thing. And then also that OD buffer distance. So those are, but when we think of it, it's fairly simple. I mean, look at a 4-step travel demand model, the big complicated one that Seattle uses right now. The number of calibration parameters it's like a whole list of so many things that have to be calibrated. And we're looking at 3 general things that need to be calibrated: the origin destination multipliers, the route impedance, and the OD buffer distance. And just as an example, I just pulled out one. This is the OD buffer distance, and this is showing the vertical axis is the R squared value, and then the horizontal axis is well, if we change that buffer distance. But again, we're not doing a dynamic buffer distance like Jonathan said. This is just the buffer distance for all origins, all destinations. And you see that the R squared peaked out. Right now we're getting to about 0.62. And if you're in the bicycle pedestrian world, you know that that's significant. To get a 62% R squared on bicycle estimation is amazing. And we'll get normally like 20.2 or 0.30. So we're really excited about that we're doing so well. With pedestrians, we're not quite as well. We're up to about 0.49. But the peak happened at buffer distance when it was at about 1.5 for bicycles and at about almost a mile for pedestrians. Again, that sort of makes sense that that's what's happening here, because it's limiting. It's saying that as you get further, the likelihood of people biking is now common. And so it's sort of maximized out at about 1.5. And for pedestrians, at about a mile, which is also what other research is saying should be happening.
So, Mike, this, like R square is based on what? Like your count points?
Yeah, the observed against the estimated.
But, you know, like this kind of model, and so when you try to say, put together a regression model, sometimes you want to adjust the parameters, which we include, which do not include, so you can get a good R square. So my concern on this kind of work is you could optimize your observed points, but there's still a lot of not observed things. Like while you optimize the points that you can compare, how is that change the other portion? Unless you get enough observation points, right? You can give a general assessment of the full network. But this is normally not the case. And how is your model relevant to, like, because you provided initial input? So how many counts, like the number are needed, like the count points are needed, so it can produce a reasonable result. Ideally, if you count every intersection, every link, right, you got an observation, and then that would be ideal. But certainly that's very costly. Do not do that, but if you have any guidance on, at least you need to count these things, provide input, so the model will give you a reasonable result.
Yeah, that's a great question. I should have realized that being a statistician here would recognize that you actually are being disingenuous if you report an R squared that's for your full data set, because you can manipulate it to get it to work that way. So the better way to do it is to actually have an out of sample and then within sample.
Yeah.
And we feel like we're at the stage of where we're just trying to understand the model a little bit better. But when we have it in the code where we're able to say out of sample R squared and within sample R squared. So what we'll do is we'll say you collected data at 50 locations, that will randomly select a subset of that. We'll run our model and calibrate our model to that, and then use that model against the control data, the out of sample data, and get the R squared for that.
Yeah, this is also a tough balance of how many inputs, like let's say you have 100 count points. If you want to do 50 as it should be another 50 as the verification point.
Right.
Perfect. But why is 50? It's like if you have only 10, are able to use them all, and also depends on where you come from, right? This is such a big network.
Right.
So I think maybe your work could provide some very meaningful results.
Yeah, well, that's great, actually. And to be honest, the whole reason I wanted to come here to do this presentation was to get these ideas going to do collaborative research. So to talk about the next PAT-Trans collaborative project and or other things that you guys are working on, any of you. So as you're thinking of this, think of how could your work maybe relate to that's actually my goal. Yeah, we haven't begun to look at that validation process of what should your out of sample size be. Often it's 10% of the data, but it might be something else. So we will start looking at that. And then there's also the question of not only out of sample, but is it transferable to a whole other city or model, or do you need to recalibrate for that model for that city? So that's for future research as well.
Yeah, so I think maybe afterwards we'll have to go to the traffic market over here. So Mark, if you have time, maybe we can go out together with visitors.
I have a UFL lunch meeting 1 to 3.
Okay. You already have that.
I already have that.
So in this case,
till about quarter till.
Okay, I think maybe after this we go to a quick lunch and come back. We can show you the work we have been doing. Maybe you know already show Haizhong. You probably can our work, right? Are you? Okay, maybe I can show both of you together. Jonathan, I hope you stay here as well.
Okay, so I have 3 more tools. They won't be as long because you've got a lot of the background now. But I do feel like I probably need to go fast. So please, I hope I don't take further time. I'll go as quick as I can. So the next tool now is going to be basically the same thing, but now we're estimating it for cars. But there's some things that we have to tweak and do a little bit different, which I'm going to explain. So AADT, if you're not familiar with that term, is the average annual daily traffic. It is something that planners use all the time. Operations folks maybe not quite as much, but we do. This is downtown Moscow. Our AADT on Main Street in Moscow is a whopping 5,000 people a day. Actually, it's kind of a lot for you to think of Main Street in a small town. So that's our average annual daily traffic in Moscow. So what we're going to do is we're going to estimate the AADT on all of the streets of the whole network. And the way that this is done in practice is we go out and we put down pneumatic tubes. Now, there's lots of other ways to count cars, and UNI has developed a lot of really neat, sophisticated ways. But the fact is that across the country, the most common way is pneumatic tubes being laid down and counting cars. And usually the way it's done is that there is a permanent counter somewhere in the city, and that's there counting all the time, 24/7, 365 days, just all the time. And then there are some short duration counts that are being moved all around the city, and they're counting. Usually, it's actually typically just for 2 days. So they'll count for 2 days, and then we'll use that to get our estimate. Well, the thing is moving those short duration counts is actually kind of expensive. And for a small town like Moscow, Idaho, and most medium and small communities, even big cities, actually for anyone, it's expensive and time-consuming to be going around and doing all of these short duration counts. So, as an example, in Moscow, in the last 7 years, we've only done 341 short duration counts. These are all the short duration count locations. And you wonder, wow, that doesn't seem like very many. But it's because they don't really have a dedicated position from the city to go and do these. But they've gone around and they have counted these 340 locations in the last couple of years. And that's going to be our data set that we're going to work with. And then you can, and by the way, you adjust it. So you adjust it on day of the week, you adjust it on the month, and then also you can adjust it into future years with the growth rate. So even though it's maybe from 2005, and in Moscow actually, we're using a data set from that long ago, but obviously they've been doing it for years. In fact, they have a GIS, not GIS database, they have an access database that goes back to the 1970s. So they've been doing it for a long time. But we're just kind of looking at the recent years using that as AADT. And again, as some background, how is AADT usually measured, estimated? 2 ways. One is some complicated multi-behavior demand model, a 4-step model, or a direct demand model. And once again, we're going to sort of combine those 2 ideas together in our method. So, some things that need to be said about cars compared to bikes. With cars, we now have this issue of trips coming from outside the city within. That also happens in Moscow with bikes and PEDs, but not nearly as much. In fact, in Moscow, the city of Pullman, which is Washington State University, is 9 miles that way. So we do actually have some bike and PED travel to the 2 cities. But for the most part, for bicycles and pedestrians, we were able to not worry about external trips. But with cars, we definitely have to start thinking about external to internal trips. And then there's also internal to external, people leaving the city. And then there's also external to external, so cars that are traveling just through the city. And that happens a lot in Moscow because it's a highway that's going north-south. People just go right through. And then there are those internal trips, origin parcels to destination parcels. And so what we're going to do is the exact same thing, but our model is just a little bit more elaborate because we're going to collect the data, we're going to calculate OD centrality, and then this time our regression is going to have the centrality of external to internal, internal to external, and so on and so forth. So all of the combinations of the internal and external trips. We're going to have these 4 explanatory variables. And again, we could have more. We could say also the functional classification, the speed limit, some other thing. But we have anything to as a regression. But we'll just look at centrality as explanatory variables of okay. So go here. Let me just turn these things off for a second. So here is again the network for Moscow. In the last 7 years, we've collected data at all of these short duration pneumatic tube counts. And here's our external gates. Those are also pneumatic tube counts. And what usually the word for when a count is on the outside is either called a gate or it's called an external generator. And it's also the AADT that's counted there. And I've just shown that one bigger or smaller just because that was kind of interesting to see that way. Those are the external generator counts. And then we have the all of the parcels with the internal trips. Okay. And we're going to estimate ADT. So again, I need to know where's my count data. And I have
format the count data and also the partition.
Yeah, there's some, but it's
to explain like this is the point I counted. This is how
yeah, it has to be organized in a certain way. It's not very complicated, but it has to have the latitude, longitude, and then the timestamp in the count. So it's pretty basic.
Direction as well, right? Directional.
And well, for ADT, unfortunately, in Moscow they don't have the directional. I just have the count. It is ADT.
If they're just stringing across standard tube counts, if they're stringing across the whole road, they don't know the directionality.
Yeah, but it could, again,
There's a two there. Two counts, right? There's a two there. You can tell the direction.
Yeah, the ones we do, but often in Moscow they don't. At least they don't keep it in it. They should, but they haven't. They don't keep it in there. They just do. But so counters with ADT. So Moscow Street Network. We have the directional field. Is direction, impedance field, impedance, internal ODs. This is internal parcels. The internal multiplier. The external ODs, that's the gates, the external gates, the external multiplier, and then again the SNOP, so it's ADT. And again, it's preparing that input. I'll show you the code just for a sec for the sake of seeing it. But yeah, it does have some format. And then it's calculating all of the trips then. All of the internal trips, all of the internal, external, all of the external, internal. It's calculating hundreds of thousands of storage paths actually. But it's a very, very fast algorithm that we adapted from this guy. He's Swedish and it's known as the fastest storage path algorithm. It works off of Jakarta.
Thanks.
Yes.
That's a very old one.
It's a very old one, but there's someone who's modified a computer science guy who's got it really, really fast. So it's calculating centrality, and now it's estimating the ADT. And as I say, the Puget Sound Regional Council right now for the city of Seattle, their model that does this takes 8 hours to run. So that was about a minute. They do get a little more data than we do, but for a sketch level planning, there we have now the ADT. Yeah.
I mean, do you know what the order of how many nodes do you have?
Yeah, well, we can just do that really quick. Open attribute table. So 5,800 So now 5,825 times
And try them on a larger network.
We had it.
It still might take you 8 hours to run Seattle.
Yeah, but I'm going to guess it
It's
won't.
exponential and, well, yeah.
But I do need to look at it, but this algorithm is really fast. Oh, I don't use ArcGIS. Yeah, I should mention that. My interface is ArcGIS, but we've written this. I'm not using any of ArcGIS.
So your routing functionality is not based on Arc, right? Your routing functionality comes from an external Python script, right? So you're doing the routing actually in Python. Right?
Yeah.
Okay.
Let me just.
Because Arc has a routing package, and I don't know if you're using it.
It's terrible.
Yeah.
So, if you are familiar with, let me just. Hold on. Wait. One second. Let me just. Oh, no, where it is. And then I'll tell you this in a second. So yes, ArcGIS has its own shortest path algorithm. It's really slow.
Yeah.
We don't use it at all. I tried it at first, and it would take like 2 days to do what I'm doing. And then what I did is I found this open source shortest path code in Python, and actually, if you're curious here, I'll just tell you because the only one maybe that cares about whoops. See. So it is. Oh no, wait, that's wrong. Sorry, let me just look that real quick. It's this guy, Ulrich Brand. You heard of him? No. Anyway, I use his, and it's from this paper, Fast Algorithm for Continuous Centrality, and it's very, very fast. So here's our, but just to get a sense of our code, then, we've written everything in Python, and it's thousands of lines of code, but that's how it would actually be quite fast. We're just using ArcGIS actually as a visualization, but all of our algorithms are outside of it. So that's AADT.
So when you do the calculation, do you consider the capacity of the segment or some congestion happening?
Oh, yeah, that's a great question. At this point, no. But it does not, the shortest path is just all or nothing, regardless of other volumes. But that's another place it could be improved. That will actually make it a lot longer to design and calculate a little more. So as I said, I didn't maybe mention this, all 4 tools, they also print out a bunch of statistical data in a text file. And so like for this one, this was the R squared for AADT, that output, and we're getting about 6.68, which is also pretty darn good for estimating AADT. And like here's the p-value, it would just have regular, it shows all statistically significant of those explanatory variables of centrality. Although centrality for external internal wasn't statistically significant. Again, this is all part of the research we're doing of why that might be, but the other ones definitely are explaining the AADT. They're really proving to be good explanatory variables. So what's the current work here? Again, improve the statistical approach. Maybe it should be a more count data regression rather than a ordinary squares. Collect data from other cities, compare the results to a traditional 4-step model, and then again, this question I think Yinhai was saying is, well, how many short duration counts do you need? So like we tell a city, here's this great tool, do they need to go out and collect 350 locations, or would they have been fine if they strategically, stratified random count of certain parts of the tree?
I think there are 2 questions here. Number 1 is how many, right? Number 2 is given this many counts you can afford, where to count.
Where to count, yeah. Like should they be on arterials? You're going to have to capture everything. You're going to have capture locals and collectors. You're going to have to capture arterials. And so how many arterials, how many collectors, how many locals are you going to need? So that's what that is. Now I will go into the third tool. And again, these tools might feel like they're all the same, but they are all doing slightly different things. So this one is actually a different problem. And so in a way, just sort of forget everything I've been saying and think of this whole new problem. This problem is a really common thing that happens where we put 2 counters down at the 4 legs of a road. And what that does for us is we now, and again, as Jonathan was mentioning, we have to have 2 tube counters at least for one line. So now we've done that. So now we have entrance counts and exit counts at all 4 things. And this happens all the time. Like the city of Moscow just did it for their transportation plan. They went all over the town And you know what they usually do then? Because what we don't know is who turned. So this is a common problem in traffic engineering, is what were the turn movements? And right now, the most common way that's done in practice is some experts say, well, I think 50% turned right, 20% went straight, another percentage turned left, right? So there's something. Now there are in academia a lot of sophisticated ways that people have done this. Were you going to say something?
So for a lot of the models of tube counters, especially the newer ones that are electronic inside, will actually have time-stamped times when the hits are detected. So if you actually can get the raw data and not the processed stuff that they hand to the engineers, you can usually directly figure it out.
Well, with some error. But yes, there's a lot of methods if you have those all time-stamped. Some of the problems that you run into is, first of all, your timestamps have to be perfect. Also, if you'd also have some sort of control where it was permitted lefts and rights, because otherwise, if this timestamp happened at that timestamp, you don't actually know, was that car the one that was turning left or the one going right? But there's research on this. This is actually a huge area. I think you've done some OD. This is actually a small-scale OD estimation. Nancy Meehan did a lot of this stuff, and Gohoi too, I think. But there's a lot of techniques out there. In general, what I'll say is, without going into the background of existing methods, is that they're really sophisticated and sometimes require a lot of extra data. And we're gonna do this again quite simply. What we don't know is the turn movements. We have the entrance and exit, but what we also have is that centrality. So again, it's coming back to using the centrality in these innovative ways. So what we're going to do in a very simple way is, the first step is use the centrality proportions to calculate an initial guess. And then the second step is to use this algorithm called the RAS entropy algorithm. Is anyone familiar with that algorithm? It's just a matrix balancing algorithm. And so we're going to use that algorithm to iterate through from that initial guess into a final solution. So, okay, so again, here's the street network, and we're going to go to, so we're going to, here's how the practitioner would do it. They provide that. It has to have centrality already calculated. That's why this will be a little bit faster, because centrality is already calculated. Folder of intersection counts. Okay, and then we'll say that this one doesn't have ground truth. And so this is like how a practitioner would try and estimate it. So we'll call this turn movement. Okay. This one, again, the centrality was already given, so it's considerably faster. I didn't have to calculate all those OD connections. 10 seconds. And this is the output then. When we zoom in on an intersection.
So this calculation is intersection by intersection?
Yeah, you could provide as many intersections as you wanted. And it does, yeah, intersection by intersection. Yeah. And this intersection knows nothing about any other intersection.
Oh, okay. Because in your previous, the second tool, actually, you already calculated the network flow, right?
Correct.
In that, I think you already, at the intersection of the connectors, you already know how many percent are turning different directions.
We do, but this way now it's able to isolate, in case there's error at other places, it's able to...
This is more accurate at the market cost level.
Exactly. And so then this is the output it gives. So I took those entrance and exits, and it just estimated all the turns.
Could you also check out if the previous system has
Previous methods?
Yeah.
We haven't done that yet. And actually, I should have mentioned this. So of the 4 tools that we have, it's the first tool that is most developed. And as I get through, down to the 4th tool, which I'm going to show in a second, the least developed. And so again, this one is number 3. So it's not quite as developed. But this time, so let me show you what would happen though now for if you actually had ground truth data. Now it's going to be able to do this in R squared. Because if we didn't have ground truth, we couldn't get R squared. But we're now ready to do this. So then we're going to do this. We'll call this intersection error, and then we'll call this one again. I just have to do it again, but let's get a turn movement 2. And now I'm running it. Now this time it's doing the same thing, but now we were saying now compare that to the ground truth data. The reason we separated that out is just to say, well, practitioner doesn't have ground truth, so what did they get? So we get that. And now if I go like this, this is all of the intersections with their R squared, and you can see we got pretty high R squared here, 0.944. And so then I can go, it also created this thing you can pull out. So, and then one of these here like this. So there's now showing the observed and the estimated. And you can see they're pretty close. And then the R squared in the middle for that intersection. And again, this is all in sample statistics, but we could make it an out of sample.
So in your calculation, you consider actually the attractiveness of the destination. Did you also consider the capacity intersection or at different links?
Only in we don't, but that's part of the impedance. So if we had on the impedance maybe that this is 3 lanes and so it has more capacity, and somehow that changes the impedance, then we could. So yeah.
Is the impedance like a fixed number or is
for cars, the way we were doing impedance is just travel time.
Yeah, but sometimes there may be a possibility you do the calculation and see the number of vehicles assigned to a particular link is actually exceeded.
Yeah, we could change the impedance then to account for capacity.
Yeah, or maybe put another level of constraint, right? Modifying the attractiveness of the destination.
Yeah, probably the best place to put capacity levels in the attractiveness and destination, the origin destinations. We want to keep those fixed, but we want to say the route to get to them maybe is constrained by capacity on the network. And so that could be done very easily with this model, just by changing your impedance to account for the shortest path capacity. And then, like you were saying, you can make a dynamic capacity constraint.
Like in this particular example, it looks like the left turn from this with the north direction, right?
Mm-hmm.
It looks like it's a estimated popularity.
Yes. Oh, right. Yeah. Yeah. So let me just maybe end this tool. Well, hold on. Let me get the next tool being open while I end this presentation with saying, oh, there's our R squared. A lot of 9s. So that's exciting. But just let me sort of answer this by saying, where you're going with this, how else could this be looked at? And that's what we're doing. We're analyzing different time periods. How does it overestimate at certain times of the day? Again, does it overestimate maybe on arterials or minor arterials? And then this is a kind of a technical thing about topology is it working in if I have time, I can talk about this because it's actually quite interesting. The comparison of a grid network and a what they call dendritic, where it's like cul-de-sacs and curvilinear streets, suburban neighborhood compared to a grid, which I'll talk about. Hopefully I can touch on that if I have time. And then also, well, what if the data came from something other than a pneumatic tube? It was a root detector or something. Those are the other things we're looking at. Okay, so really quick, this last tool, this one goes really fast because, like I say, it's not as developed, although it's going to look cool. It's a lot of prototype of what we're wanting to do here. So, but let me back up real quick, just to review what we've got. So centrality is this calculation, and this is the significance of what it is. This topological measure is able to give a number to every link, a real number, so real, it's quite, it's not an integer, it's a real number given to every link that represents the importance of that link in the network. So now we can begin to relate every link to every other link by this measure of centrality. And if you've been to Moscow before, you can just see that. You know that it's showing that the high red centrality is where the highway is. So this calculation was based totally on the topology of the network, but it's able to see this. Okay, so because we're now able to connect every link to every other link through this measure, this is where we're going with this now. All right, let me tell you what we've got here. So this is the net in black is the network of Moscow. We have some ATR locations. There's 4 of them in Moscow. They're at the edges of town. There's 4 ATRs in it. Annual traffic recorder. It's a permanent traffic count. So we have 4 of those in town. Then we've got, these are all the loop detectors in Moscow. We have 78 loop detectors in Moscow. And then we have 7 Bluetooth devices that we position throughout town. So those are in blue now, it showed. And then the University of Idaho also has a weather station. Now I show these ones, but we could have other sensors. So just think of these as sensors, different types of sensors. Okay, so now what we're going to do is we're going, oh, I already got it. I want to estimate. Okay, so this one, and so the reason I've chosen these ones is because Moscow, the University of Idaho, I mean, we have a connection to all of the loop detectors. It's a fiber tube that's telling us what those are doing in real time. We're actually getting data every data status change every 10th of a second status change. So it's really high resolution. Lots of data coming from all this stuff. And if you had Bluetooth, wireless, and everything. So let's say we've got our database. So you connect to the database. You say your start time. Now we have some study data for January 29th. And we're going to change this to 6 a.m. to, okay. And then now we say the end time, and then January 29th to 8 p.m. And then now here's what sensors do you have? So we've got the permanent loop detector, or sorry, tube counters, and we've got the loop detectors at all the controlled intersections, the traffic signals. We have Bluetooth sensors. We've got the weather sensors. There's our output folder. You can go to output. Okay, and then which performance measures do you want to do? And right now we're just playing with these performance measures: volumes, VRC ratio, and pollutants. Querying the database. Now this one again is not calculating centrality, that's already given, but it's now using that centrality to calculate performance measures and then prepare some animations. All right, so that one ran, and let me just zoom in a little bit more here because it's pretty cost sensitive. Let me just turn this off now. It estimated the volume, so let me just show you. If we go here, so that's what's coming in, all of the detectors and all of the occupancy that's happening. The phones are the Bluetooth. I use that as my personal Bluetooth station. And then you see the weather is coming up every hour. So this is all the data that's coming in all the time. And let it run here. So then if that's running, because we're able to, let me change this to 60 minutes because it'll bog it down if I don't. So 60 minutes. And also let me turn off. I'll turn off this one. Yeah, I think I can do it. Let's try it. The bar is down. I'll have to turn it off. Here's the street volumes. So then now here is the hourly street volumes. It's kind of hard to tell, but those are changing. Here, maybe even let me So now we're trying to estimate the track volumes at every hour based on what's happening at all of these detectors everywhere else. And then let me go here. Is there any questions on that? Let me go on here. So we also know this. We know that this is from the EPA. This is emissions for, well, actually, I can show you one. I'll show you a different performance measure. So right now we're playing with 3 performance measures. One is volumes. The other one is VOC ratio. So let me animate that one. So that's VOC ratio throughout the day at all of the networks, all of the streets. Okay, so now we also have, as another performance measure, we looked at pollutants. We know that passenger cars are polluting so many grams of all of these pollutants per mile, and light vehicles, heavy vehicles, and so on and so forth. So that query that we did on the database, since we now have an estimate of volumes, we now can have an estimate of these. So let me just. not a lot of room on this little projector screen. So now that is, and also I'll change, this goes too fast, otherwise I'll change it to a bit slower. So now this is the emissions over the day that we expect. So we've got volatile organic compounds, total, up in the left is hydrocarbons and nitric oxide. And we've got carbon monoxide, carbon dioxide, and then particulate matter 10 and PM2.5. And that's showing, so it's pretty clear what we're seeing here right at the peak. That was at the peak hour. Okay, so where are we with this one? This one, as I say, is conceptual really at the moment. So we actually need to make these connections. We have it. We're really close. Having these connections, all of that. Then we also have to make the prediction model that are working with all of this data to make these predictions and then analyze results. So there's a lot to be done with that one. Let me just conclude now. So these are tools. They are inexpensive, pretty easy to use, as you saw. But the main thing is they require commonly available GIS data, and they produce pretty good results. So where do we want to go here? We'd like to try and do another PAC Grants collaborative project, and we're actually wanting to focus more on, I know there were a lot that I showed there, ADT, turn movements, and then solution at the end with emissions. But right, we're just thinking we need to focus on something. So bicycle and pedestrian is one that we're thinking of focusing on. We know that Yanhai and Jaeger have been doing this with, well, we've got all these sensors out there. You've got, what do you call them, Jaeger, opportunistic sensors?
Yeah.
You know, how does that relate in there? And so the reason why bicycle and pedestrian, though, is because we feel like there's a lot to do there. Car estimation, you know, it's not as much to provide to the industry right now, but with bicycle and pedestrian, there's really nothing out there. So we really can make a huge impact if we focus in on that. So that's kind of where we're thinking of going forward. And any other questions or suggestions? Actually, a lot of suggestions. Thanks for all the suggestions. Sorry I had to talk really fast, but I know we have more time here. So.
Like any the city of Moscow or the DOT, out of the DOT, like they are somehow interested in
I hope so. we haven't started sharing these. I mean, they're all in the development phase. In fact, we're still writing papers even to publish on them. So this is hot off the press. You guys are seeing it first. So we are working toward that.
Like this tool part is supported by the Paxton's research.
Yes.
So it's in the leading.
Yes.
Yeah, I think I'm very surprised actually to see you become so computer savvy. Developing a lot of good tools. I think they are great tools. If you look at our drawing net, you will see there are a lot of similarities. But
I know. Yes.
Say like drawing net is, I would say, better.
That's fair.
Because drawing net is more like a tool for everyone.
Yeah.
This is you have your grid to running on your laptop.
Right.
So the accessibility is kind of constrained. But certainly this lays a great foundation for a lot of potential work, including the environmental health related work, because they may need the traffic activity, walking activity, and such. So I can see potentially there are a lot of things we can work better based on what you have been doing and what we have been doing. So perhaps they can allow you importing your data to the TriNet system, make it a online version.
Mm-hmm.
Yeah. So I think these tools are just step by step, which is great. Actually, I can see you make yourself pretty busy over the past couple of years.
I
don't know.
Yeah.
Yeah. And I think that this foundation is there. It's a really good foundation, and I think I was very, very impressed. So
thank you.
Any other questions, comments?
On your pedestrian data, your limitation is that you've got 2-hour counts and more than this. So what that gives you is commute traffic. So as you start to do your more in-depth analysis, it will be interesting whether you have to model your purpose, which will change your origin and destinations and your weighting, and it might also change the distance which people are willing to walk or bike. And you'll also have to worry about that as you look at the interaction of the road network itself and where your origin destination lie. So as you're predicting an AADT, an average daily value, you'll need to actually incorporate multiple kinds of purposes, whether you want more different equations to then add together that estimate bike traffic relative to work, bike traffic relative to recreation, bike traffic relative to whatever. That will, to bump that R squared up from 0.62, you're going to have to deal with those behavioral differences in addition to the street network things. They'll probably appear somewhere in your choice of origin and destination, not so much in your choice of travel.
I think that's a really good point, and maybe I'll ask you this now. See, because one of the other things is we want to balance out making a tool that a city, okay, they have parcel data, they have a network, and they run the tool, compared to, do they now have to do surveys and ask people where they're going and get some kind of mode choices? So, like, where do you think this should balance in terms of a sketch level tool that's quick and easy, or a tool that's trying to get more detailed in modeling all of those 4-step choice models? You know?
So if you look at the data that's coming out of Colorado, where they're using more automated counting equipment, the issues are that the traffic volumes, like pedestrian volumes, you see on commute-oriented routes with one pattern. You got to see this here.
Yeah.
Right? Commute-oriented patterns. This will do really well at estimating your commute-oriented patterns. You do really badly on those trails and facilities, whatever that are recreational-oriented patterns, so the weekday or the weekend or whatever. So again, in a sketch planning model that works really well on commute-oriented traffic, one thing you might want to do when you're using it, not that it's better or worse, but it will do really well at modeling commute-oriented bike traffic. It might not do so well modeling fulfillment traffic. So think not only in how you push forward in having those next things to it, but think how you present it and what they will be using it for.
This is why Mark is a data guy, because you got it right on. We found that our R squared is better, for example, on the commute type facilities, and it's also better in the morning. And that's because I think the morning commute, the bicycling is pretty, this is where I go, this is where I do. Whereas in the afternoon, they're going to the grocery store or wherever, and so it's a little messier. So that's exactly what we found.
What's in your key measures?
Right now, we're just distance, so just the shortest path. Oh, but we were looking at slope too. We actually found the slope didn't really do much for us.
You don't have slope.
But here, let me just tell you. So what we did is we had to do. We created another tool which calculated the slopes on every link. So you bring in the digital elevation map and then it would calculate the slope. We did it. We actually didn't really find it too much, but again, maybe it's Moscow, pretty flat. Although the hill I have to ride up to get to my house is pretty steep. I think.
What's the maximum elevation or the max grade that you're seeing?
Oh, max grade. Oh, I can't remember. I'd have to look at it, but
I think I have to cut it here. We have another speaker. Let's get much. I think we still would continue our discussion on her lunch. So now I would like to invite Dr. Haizhong Wang, who is assistant professor at Oregon State University. Haizhong got a PhD from University of Massachusetts honors. What year? 2010. 2010. So you moved to Oregon State last year, right?
Right, last summer. I hope everybody had a happy Valentine's Day last night, right? Okay. The presentation today, I really want to share, some of the empirical findings from data. It's actually on Georgia 400. So the goal is actually from the empirical finding, that how can we model the vehicle variance? The variance, what can I do for is using that, right? Yeah. Before we, look at the data or the model, I would like to share the modeling philosophy. I appreciate it very much. It's essentially all models around, but some are useful. Like Georgia box, many of you have heard this before. and he's a statistician. I'm not sure if he's alive or not. So what caused some of the models are wrong? Like in transportation, we have driver behavior heterogeneity and vehicle heterogeneity. And the presentation today, I would like to focus on the empirical traffic speed variance and show some of the simple models and achieving two goals. The first one is the empirical accuracy. We want the model to represent the empirical phenomenon or the empirical nature. At the same time, we don't want the model to be too complicated. Mathematically, it should be easy to use. My goal is using just one formula to capture the variance, the structure. And like I said, the data is from a Georgia 400, which is actually a corridor. It's about 20 miles long. It's entering the city of Atlanta, Georgia 400, about 17 miles long. So you can see from here, you cannot see from here, but it's actually the northbound and southbound is intersecting with the road 285. That's 285 circling the city of Atlanta. It's actually one of the busiest roads in the U.S. This is reproduced from the Google map, and this is the setting of the detectors. This is the virtual loop detector. The data is from the Georgia DOT ITS program. They had 100 cameras, on the 17 long corridor, and 78 of them are on the basic highway segment, and 22 are on the on ramp and off ramp. So 11 on ramp and 11 off ramp on both directions. So this is the data where data came from. The data I have is from 2003. Well, a little bit 10 years before. But the data is pretty good because it has the vehicle classifications. We have the passenger cars, the vans, and also the heavy vehicles. One limitation of this data set was because you're using the virtual loop, many of you know that, right? Virtual loop detector and get the data. So it's aggregated. We do not have the vehicle-specific information. For example, the speed has been aggregated in over 20 second interval. So we lose actually the resolution of the individual vehicle's information. And let's first take a look at some of the why Wang wanted to share this research. I would like to point two literature. The first one is the speed variance and influence on accidents by Nicholas Faber. A lot of people know this name. He's the author of the textbook, Traffic and Highway Engineering. And that research was supported by the AAA Foundation a long time ago, in 1988. And another one, relatively recent, is conducted by University of California, Alvin, in 2004. It's trying to identify a relationship between the freeway speed variance and the vehicle heterogeneity, lane shading, those types of information. And the third one is actually an interesting paper from American Economic Review. The key point from that paper was the speed doesn't really kill, but the speed variance kills. So I will leave the other few. Let's take a look at first some of the takeaway from the literature is, like I said, the speed doesn't kill is from the economic paper, and the other two is traffic safety is a function of speed variance from the speed reaching study. Another one is speed variance is actually a functionality of vehicle heterogeneity, and driver behavior can understand driver heterogeneity. So different group of people who are aggressive drivers, some are cautious drivers, right? And vehicles, different type of the vehicles in the traffic flow. And the last one is actually Nicholas Faber. He found from the study that the first one conducted in 1988 is the speed variance will be minimal if the posted speed limit is between 6 and 12 miles per hour lower than the design speed. This is empirical result from this study, but that has been over some recent study that over the past over 20 years, is there any change, right? Hasn't found any relatively recent study yet. But let's take a look at a empirical.
Haizhong, I have a question about Nicholas Gauber's
Yeah.
about.
Yeah.
So number one, I think it's very hard to know what was the design speed. Right? So how big was his sample for his conclusion in his paper? So how many rounds or how many design speed, what the segments did he use?
I can double check, but in the report, at that time, the sample size is not very large, to be honest. It's not very large. And so whether this is from his report, not sure, if we do another study on cellular nature, whether we can provide the same conclusion or not.
I think these variants could be affected by several things. Not
Yeah.
just the difference between people.
Oh, absolutely not. Yeah.
There's also if you have a grade.
Yeah, the geometry.
How often you have incidents. I think those things is more important than I just feel it's maybe some a little bit arbitrary.
Yeah. I feel the bias I give to the driver heterogeneity, the vehicle, and also the geometry, even the weather, a lot of other factors. But the problem is a lot of factors are very hard to quantify. They're very hard to quantify in a quantitative manner to incorporate into the model. And that's my understanding. And let's take a look at the empirical one. I'm sure that everyone of us know the left-hand side is a speed-density relationship over a long time observation. So this is actually over a year, aggregated over a 5-minute interval from the station. I believe it's the 4018, one from the 78 on the basic Fourier segment. And everybody knows the differential model, right? The differential model, initially, he actually collected 7 data in 1934 on the Michigan rural road, 6 data from one road, but he not collect enough data using the camera itself, but collect another one because on that rural road there's no congestion. So the 6 data is actually in the free flow phase, but the 7th data from a different road and put it on that and come up with a linear relationship. At that time, that's already that's the first one. That's why we feel it's the origin of the key to transportation engineering analysis. And so this is the over a year's observation. We can tell that it's not really a linear relationship. That's not the focus of this, of this talk. But let's take a look at the picture on the right-hand side. The red curve is actually the mean. The red curve is the mean of the empirical observation. And this blue curve is actually the variance. So if we draw on the horizontal, the x-axis, we find any density, right? If we draw a vertical line, and this vertical line will pass the empirical observations, right? The empirical observations, based on Greenshield's model, we know that on each density we have one speed, right? But empirical, empirical data shows a distribution of speed instead of one. So if we calculate the variance at each density, and then we come up with that blue curve. That blue curve is the empirical curve. You can see that it's not smooth, right? But in general, we can tell that the trend is about increase first and then decrease. And the point to maximize the variance is interesting is here, right? This is the maximum variance, and this is in the vehicles per kilometer. So this is about the critical density that we used to use in traffic flow, right? So, and this is the variance structure from this one station. But let's take a look at other stations. Is other stations demonstrating a similar structured vehicle speed variance or not? And This is
Haizhong is the biggest one. This one, like, to the right figure, the density is the number of vehicles per kilometer.
which one?
So the unit of density is vehicle per vehicle.
Oh, these two figures is actually from a different station. So that's why you see, from the horizontal axis, it's not the same unit. The first one is from 0 to 100.
I wonder how many that figure is probably miles. Because otherwise, the critical density goes too high.
Oh yeah, that's in miles. I'm sorry about that. Yes, it is.
So how many lanes too?
This is in this station. It's 4 lanes in one direction, but it's aggregated. It's already converted to a per lane, so into per lanes. And for this one, for this data set, we do not have the lane-specific information either. So it's all converted to one lane. And
that explains.
Yeah. That's right. Good point. And if we look at another station, which is actually the station number is there. So this is over weekly on weekdays from Monday to Friday. If we plot the observations over a year, and we can tell that the structure of the variance is actually preserved on weekdays, right? From Monday to Friday, it did not really change much. Increase first and then decrease. It's not a smooth curve, but when we model it, we will use the smooth curve to approximate that empirical one. And the difference, what's the difference? We can tell from here, the side curve. A similar structure, right?
The peak for Friday is lower.
Right. The peak, the location of the peak, we can tell from the location on x-axis. It's about the same location from the density for 35 to 40 or 35 to 45. But the peak, it varies from over the weekday, Monday to Friday. And this is one for on northbound. And let's take a look at one station on the other side. So we can tell the structure still preserves, right? On the weekdays, from Monday to Friday, are all on a 5 minutes interval. The original data is a 20 minutes interval, a 20 second interval, but aggregated over a 5 minutes interval.
How are you getting these speed spikes? I mean, you've got the speed there on Thursday that's pushing up to 180 kilometers an hour. That's pretty major, the variance, I mean. What's the unit of the variance?
The unit of the variance on the vertical axis?
Yes.
It's the speed, it's the kilometer per hour, the speed.
Okay.
This is all already converted to kilometer per hour.
So you're getting a variance in speed of almost 180 kilometers an hour on Thursday?
The data is not perfect. There may be some outliers. But there are, from the empirical observation, there are some peaks over the weekdays. And
how are you actually calculating the variance in speed?
Calculating the variance from that distribution of the speeds, right? Mm-hmm. We have the mean of that each distribution, right?
So you're saying I've got a year's worth of data, I've got an average speed of
right, the same location.
And then you've got the variance calculated from that.
Exactly. That's how we calculate the variance of the speed at each density.
Does that mean time dependent? Because, is it a fixed mean for the whole day?
It's not time dependent. We lose the time information when we plot the curve.
Because it's probably based on density. So if you're looking for the same density, it doesn't matter whether it happens at 5 in the morning or 5 in the evening.
Right.
It's plotting it by density.
Yes, that's right.
But the thing I'm looking at is if you're getting speed spikes that are speed differences that are that great,
mm-hmm.
something else is probably wrong with the data. Because if you think about it, if my speed limit is 60,
mm-hmm.
60 miles per hour, and I'm, my average is 35, I'm still not that far
mm-hmm.
from 60 no matter from 0 to 60. I just can't range
yes.
much.
In that data set, on each of the lanes, this is virtual loop detectors. So the detector status actually report is OK or no X. So I actually do a filtering of the data, like program in Python. Like if on this 4 lanes, if the 4 status of that the detector reports are all OK, then get the data. Otherwise, if the data is not, there's also another column which shows the confidence of the data. It's the numeric value from 1 to 10. Another way is we use the data confidence over 5, or you can also choose the value as confidence as 10. In general, if confidence is 10, then the vehicle with detector status will be OK. But I did actually some filtering from the raw data.
Maybe the valence 100 is okay. Still okay, because that is not the same situation. That's the valence.
Yes, it's very, it's not the standard deviation.
Yeah, it's 20.
The variance is just
Yeah,
square.
Yeah, it's square. Yeah,
You're still going to have the same situation. If you've got a really high
I think
variance,
just
then your standard deviation is still high.
Yeah.
I mean,
If you square that number,
it's 10.
Yeah.
Just 10. Yeah. Still.
Yeah.
but I mean, 10, 2 standard deviations is still going to put you on a pretty wide range. What I'm getting at is
this is a freeway.
Yeah.
I'm-
70.
I know, I'm just saying that the amount of variation you should be seeing in any given traffic condition probably isn't anywhere near that high. I mean, I wouldn't expect it to be routinely spiking to those kind of levels for a year. I mean, you're talking about even if it just happens once a day, 365 observations, that should bring down your standard deviations and average. Your statistical function should be pretty certain by that point, because you're not going to have that much variation.
Sounds like maybe if you just show it the standard deviation of variance might be hard to tell. It is hard to look at variance.
I mean, that's part of it, but it's also just a matter of if you've got that many samples, your standard deviation should still tighten up a fair amount, because you wouldn't expect. I would expect volatility at that point. I just wouldn't expect there to be that much.
It's not very regular average station average is that high, but I think we can definitely go back and take a look at the data. What happens at a certain time on that Thursday or on that day. But in general, I think the variance structure makes sense.
Yeah. I'm just curious if there's a data quality control issue or something like that.
There are the data set, like I said, it's not perfect. There are some. It's a video camera and a video data, and you put a virtual loop detector and you extract the data. There will be some errors in that process. Okay, so this is the weekdays, and if we take at the weekend data, weekend data over a year. And we can tell that the structure will be different on weekends. In general, the vehicles can travel. Not that many vehicles over weekends than weekdays. So, and this is the 2 Saturdays, and these are 2 Sundays. So actually, the empirical, the model that I will show later is actually feeding the model, captures the variance over weekdays, and it works for the weekend, but only can tell that the density is pretty low, and still with the trend is increase and then decrease, and so that's the point. And the structure, various structure, is different from weekdays to weekends. And so we want to model that structure variance, first increase and then decrease, and this is actually the function that we propose. It's actually not I propose the function. This has been used for some of the biofields. It's actually come from a growth model. Let's take a look at the data. The first one is the same curve, the mean and the variance. But the others we already used the standard deviation. So we use the standard deviation. You can tell that it's actually the red curve is empirical, and the blue curve is the model. So we can tell that the blue curve actually tracks the the empirical, and we'll use them the quantitative compression in the next few slides. And so when we get the root square of the variance to get the standard deviation, it looks much better, right? So the model actually involves two parameters, and this VKI theta is actually the mean of that scatter plot. And that's the speed density model, right? It could be a Green-Shell model. If we plug in a Green-Shell model, we know that Green-Shell model is a linear one, right? If you plug in a linear one, you'll get a parabolic variance. So that's not the empirical variance is not really parabolic, right? The increase first, and it's actually screwed. It's not symmetrical. It's not parabolic, but it's a parabolic shape. Parabolic shape increase in the first and then decrease. The maximum happens around the critical density. So this is the equation that we use to model the speed variance. And then this VK theta is actually the one in the variance model. It's the one that's here. It's the one that's here. And there are three models with the different number of the parameters. The first one is the 5-parameter model. The 5-parameter one is the first one is free flow speed. This is easier to understand, right? Free flow speed. And the other one, VP, is actually the speed which captures the empirical, the congestion information. You can tell at jam density, the vehicle speed, larger density, not really jam density, the speed is not really zero, right? In reality. In the Green-Shell model, it's in the stop and go condition. It captures the stop and go condition, not really zero, right? We only have the experience of driving in extremely congested conditions. The vehicle is not really parked there. It's actually finite movement, stop and go. And that VP is actually capturing that phenomenon, the finite movement in the congestion. And the other parameter is KT, called transition density. Is actually when the curve, it's easier to visualize from here using the transition. Is we can tell the structure of the speed density model is actually from density increase from 0 to some density. The speed is not really decreased right away, right? And you are only driver on the freeway, or there are another 10 more drivers. You can drive still at pretty low speed, right? So the speed it does not really decrease right away. That's a flat area and then decrease. And that KT captures that transition from the flat area and then decrease. That's the transition density. And that's for a 5-parameter model. The theta 1, theta 2 actually do not have the physical meaning of the shape parameter. Shape parameter, we'll show that later on when compared with the 4-parameter and 3-parameter model. And the 3-parameter model is actually reduce 1 parameter from the 2, but remove that theta 2, but keep theta 1. And the 3-parameter is remove that the stop and the go speed. Assume that the vehicle is jam density 0, very close to the Green-Shell model, but it's the exponential one. It's not the linear one. And let's take a look at the performance of the 3 models here. We can take the left panel is the 5-parameter model, and the middle is the 4 and the 3. And we can tell the difference, right? Obviously, the 5-parameter model works much better than the other 2 because it has more parameters. The shape, the theta 1, theta 2 is actually the shape parameter which actually controls the line, models the mean of the empirical observation. Now this is, the balance that we want to strike. We don't want the model to be 1,000 parameters, right? But we also want them to have reasonable empirical accuracy. So let's take a look at the performance of the 3 models when we put in empirical speed variance. This is the first one, the 5-parameter model. When we vary the parameter, right, have the different free flow speed. different free flow steps. The first curve, the different free flow speed, right? This is actually the idea of something multi-class modeling in traffic flow. It's just that different vehicles are having different free flow speeds. And if you look at some of the papers published on Transit Research Part A, Part B, a couple years back, multi-class modeling is using that different curve, speed density curve, with the different free flow speed. And second one is when we change. This one is when we vary the VB, is the bottom speed, and when we vary other parameters, how the model shape, how the model will change. And the last one is actually when we put the 5-parameter model into the variance equation, and we haven't compared the empirical data yet. We'll do that in the next few slides. But you can tell, and this empirical mean and the 5-parameter model works pretty well. And we vary the parameter in the variance function, this curve, increase and decrease. So we can control the parameter to make the model to capture the empirical variance structure. And it's the 5-parameter model. And then this is the 4-parameter. The first couple of slides is really the same thing. We vary the parameter, how the 4-parameter model change. And the last two is actually the 2 parameters in the variance equation. When we vary them, how the variance function change. Obviously, this is a smooth version, right? Mathematically elegant. But the empirical one is actually not a smooth curve. So it's the 2 parameters of the 4-parameter model and the variance. And the last one is the third model, which is actually less number of parameters, but it's the empirical accuracy decrease. And we can tell that from the validation. And the first 3 slides is when we vary the 3 parameters of the 3-parameter model. And this is the variance function. The 2 on the bottom is the variance function that actually how it change with the tau and delta. These are 2 parameters in the variance function. How it change with the parameters. And let's take a look at how the model performs when we compare against the empirical observation. This is the comparison at a detector. This location is actually on a basic freeway segment. And the first set is the 3-parameter model. 3PL means the 3-parameter model. And the blue one is the model, the blue one, yes, blue one is the model, and the red one is the empirical observation. The red one is the empirical observation, and we can see that the 3-parameter model, has the difference between the model and the observation is larger, and we can tell this from the arrow. This is with the model residual and the various residual, and we can tell from. And this performance is consistent when we vary the location from one detector to the other. And the last one, this is the 5-parameter model, how it performs. And we can tell that it actually generates a smaller error across the board. And when we vary this to other detectors, this is geographically pretty close. The 18 to 19 is just like 0.5 miles apart. And we can do the same thing to compare the empirical one under the model with the 3-parameter model and the 4 and the 5. Obviously, the 5-parameter model works the best. And then compare more comparisons to other stations, and we can see consistent behavior. And one more here. And so at this point, we're relatively confident to make conclusion that the proposed actually the variance function works, right? It works. It captures the empirical variance, first the increase and decrease, and with the relatively reasonable mathematical accuracy. And if we compare these models to other models, for example, the Green-Shield model, to the Underwood model, those models developed after the Green-Shield model, And this is the one that we proposed here. You can see the error is actually much lower across the 39 basic freeway segments, the 39 detectors on the northbound, on the southbound, and the northbound. So the model works better than some of the existing models. And with that, I would like to, share some thoughts, potential, collaborations we can do together. Like I mentioned, this DriveNet platform, there's a lot of data available. Whether we can, from that data set, and using some of the analytical way to, this is some of my thoughts, what we can look at or open for discussions for sure. And I'm proposing this because the speed differentials is actually, a lot of people are interested in that. If we can reduce the speed differential, it reduce the risk of the accident, right? And also reduce the accident rate. And another one is, put it in a worsening scenario. The worsening scenario, how do we do worsening speed and queuing control to minimize the delay and minimize the speed difference in the worsening scenario? And measuring the safety impact, it's currently a lot of people do it in a qualitative way, whether we can do it in a quantitative way to measure safety impact. And this accident rate and injury severity model. And currently, the injury severity model, people are using the discrete choice, model, including the land use and including a different number of the parameters, the considerations. Whether we can use another way, starting from the speed variance, look at the injury severity. But this, if we want to do this, we need a lot of empirical data. It's actually, I think, a deep data set. And also on different facilities, freeways and arterials, other facilities. And some of the quick conclusions here is the empirical observation, so the structure, the speed variance, and the variance over the weekdays is different from the weekends, the structure, but somehow it's consistent. It's just using the first half of the function can be transferred to the weekends. And the proposed function works based on the comparison we did with the empirical observation. And this can lead to a stochastic fundamental diagram. Right? We use the Grecian model is just a one single curve deterministic. So with this, we can generate a scatter plot using an analytical way to model the fundamental diagram. It's a stochastic fundamental diagram. So with that, I will stop here. Hopefully, there's still on time. Good job. Any questions? I hope that we'll still keep the work.
Have you considered using some other distributions, like something like a gamma distribution, to get your behavior to tail off?
I did not try it, but when we look at the various curves, it does look like that.
You should be able to set a set of parameters to give you that initial low.
But we also want the parameters to be physically meaningful. We just using parameters, we can vary the distribution to fit the curve, but we also want the parameters to be physically meaningful. For example, in this one, the model is physically meaningful. Parameter is, for example, the one here. This parameter here, this one is when this speed here equals the free flow speed. When equal to free flow, this will be 0, right? And this will be 0. And this parameter is actually when the density is approximately 0, the speed variance. The speed variance, which actually can be captured from here. Or standard deviation is somewhere here. So these parameters are physically meaningful. If we use the physically non-meaningful parameters, it's very hard to justify.
How do you calibrate your alpha?
How can you determine the alpha?
Oh, the alpha. It's actually that's a good question. I use the least square algorithm. This parameter, to be honest, I haven't found the physical meaning of that. It's a small number. It's a small number across the. I didn't put it in the slides, but I calibrate all for the 78 based on basic Fourier segments, and that number is in a certain range. It varies, but in a certain range. I wouldn't say it's a constant, but we can put it as a constant. But it actually varies based on empirical data. This curve has been used to model, like for example, lots of people, the patients taking the different dose of the medication and the effects of that medication. Or in the biological field, we put the different type of fertilizer or ingredients for certain plants, the growth. As long as the response to the input variable is a logistic curve, it's a logistic relationship. It's dramatic. I wouldn't say this is a model I can develop. It actually exists. First developed in 1800. Very long time ago, 1834. I'm a mathematician, so I just used it in this context. This is not really something new in the literature. So I just put it in the transportation context and found that it works. It works. Any other questions? It's obviously a little bit different than the work Mike just presented, but I can see some of the connections even similar to different topics.
I think there's this kind of an overlying theme of trying to manage complexity. And have something that you have a fairly complicated kind of set of, right? So you can keep getting more complicated, right? You can have more variables, right? And Mike can have more explanatory.
Right.
Trying to come up with some sort of kind of.
Right. That's why I'm saying, we want to achieve the balance between the empirical accuracy and the mathematical elegance. We don't want to use 1,000 parameters, to get a curve.
You might not be able to.
Obviously, we can do like a polynomial, right? Very a lot of parameters, but that's not really attractive mathematically. We want to use a relatively simple, like one equation to capture the structure, and then with not many parameters. Like this one, only 3 parameters, 4 parameters, 5 parameters.
So you need to be able to extract some base level of utility based on the kind of amount of complexity that you're willing to do. Right.
Yeah, from that perspective.
The expense of collecting the data.
Exactly.
Right.
You could have more data, of course, but as tight as possible.
Mm-hmm. Mm-hmm. And I think if we have like a data set which can give us the class specific, for example, we have the individual vehicle information, passenger cars, the vans, and the heavy vehicles, that'd be great. I have been looking for that data set for a long time, but I haven't really found any. Over TRB, I get the impression that right now a lot of people are moving towards the class specific. Right now it's still aggregated. We lose the resolution of individual vehicles information. We only get 20 seconds to speed aggregated together. We can have that information great. I talked to Karen because when she was working in Georgia, she told me that she has data like for the accident rate on this road when this data was collected. Accident rates and also the geometric information was recently to get that.
Any questions, comments? So anyway, I think very interesting talk today. I really appreciate both Mike and Haizhong for spending your time traveling to here and sharing your excellent research with us. And I think these two research talks are actually showing excellent research from 2 different perspectives. One is from like visualization with hiding like the mathematical work behind,
And Haizhong's work actually tackling a very important issue using simple research model. I think both kinds of work are needed, and actually we also see potential for like the startup people to work with both fields, or maybe we all work together. So you see, like basically, I think one important trend in today's research is actually move away from a very tiny point or segment to a much broader range, right? So like in Max's work, how do we place these pedestrians over the network with the existing information? Yeah, my work may not be 100% accurate, but can you give me a better one? Right? Mine is the best.
Exactly.
Right? So similarly, I think in this, like we have a lot of data. How do we extract the data so we can provide a very meaningful input for the, say, like traffic operators, safety managers, giving good explanations on why this particular route has more accidents or like have more breakdown. How do we control that, right? So I think when we bring these things into a larger scale,